Hello everyone, and welcome to episode 3 of the mini video tutorial series on computational models. In the previous tutorial, we concluded by posing the questions for finding the largest possible positive integer using a certain number of bits. To answer the first question, we can write out an all ones 8-bit number because it is quite small and does not require a lot of effort to evaluate the result. It should be clear that the so-called all ones number produces the largest possible integer that can be represented by a binary number, since all the powers of 2 contribute to maximizing the resulting sum. To answer question 2 and 3, however, may require a bit more ingenuity, since evaluating a 64 or even a 32-bit all ones number by hand may be a bit of an unreasonable approach. Thus, we proceed as follows. We will enumerate all the 2 bits, 3-bit, 4-bit and 5-bit combinations of ones and zeros and extrapolate the observed pattern to obtain a formula. The advantages are clear. We obtain a formula taking as input the number of bits and gives us the maximum possible positive integer that can be represented by the amount of space or memory allocated to it. We have also introduced the concept of an all ones number, which we will elaborate on in just a bit, pun intended. Next, we list out the range for each case. We can ignore the minimum of the range for now, since for unsigned integers, the minimum is identically 0. Observe that the pattern produced by the maximum is almost a geometric sequence. It involves powers of 2. Thus, we can rewrite the terms as index powers of 2 minus 1. We obtain the following formula to calculate the maximum or largest positive integer that can be represented by n bits. Now we can simply substitute the values 32 and 64 in the place of n, respectively, to obtain the maximum possible number that can be represented by 32 and 64 bits. This brings us back to the concept of an all ones number, so let us further discuss its importance in relation to binary numbers and its significance. As already previously mentioned, the largest unsigned integer that can be represented by n bits is ascertained when all the coefficients of the base 2 power series is 1. It is x subscript I is 1 for all I in the index list 0 through n minus 1. Note that this is only the case for unsigned integers. We will soon discuss signed integers, since we need a way to model or encode the concept of negative numbers into computer memory as well, for practical purposes. The concept of an all ones number in binary format plays an important role in computer arithmetic for multiple reasons. 1. It provides us with insight about the largest possible quantity that can be represented by a finite number of slots or cells. And 2, it also gives us a good clue as to how we can model negative decimal integer numbers into computer memory. Let us now restrict our attention to point 2 by discussing a technique for modeling or encoding signed integers into computer memory. First, observe from the enumerated list of n-bit numbers that for any binary number in that list, there exists a complement in the sense that the sum of the number and its complement will always add up to an all ones number. This is an extremely important observation, since from the theory of rings, we see similar behavior for numbers and their additive inverses, in the sense that a number and its negative counterpart or complement always adds up to the additive identity element. 0. Thus, in this new universe of numbers, we can think of the all ones number as an additive identity element, while reserving the complement of a binary number for its additive inverse, in the sense that it represents the negative of the original number. However, in this new universe of numbers, we are forced to associate with the all ones number the number 0 for it to correctly represent an additive identity element. By doing this, we run into a predicament. In other words, we have two distinct representations of the number 0. It is the all zeros number, 0, 0, 0, 0, 0, as well as the all ones number, 1, 1, 1, 1, 1, 1, both representing the number 0. The reason that this is a problem from a mathematical perspective is due to the fact that there is not a one-to-one correspondence between what the number represents and the encoding or representation of the number. In other words, there is no unique inverse for the number 0. Luckily, this is not such a huge problem since it's only one element that behaves in this erratic way, and the CPU arithmetic can be defined in such a way to deal with the particular case when it encounters the all ones number at any point during a computational procedure. Therefore, we are not too concerned and pretend as though our number system is perfect by cutting off the all ones number from the list's range. Let us contrast the 4-bit signed integers and the 4-bit unsigned integers to better explain some of the insights and key features that each of the new number systems provide. Notice that for signed integers, we can tell by looking at the most significant bit or the most significant digit, it is the leading digit, whether the number represented in computer memory represents a negative or a positive number. If the most significant bit is a 0, then that binary number encoding suggests that the number stored in computer memory represents a positive integer value. Whereas if the most significant bit is a 1, on the other hand, then that binary number encoding in computer memory represents a negative integer value. Thus, we have achieved the desired model implementation for encoding signed integers. It is, we are now capable of working with both positive and negative numbers when performing arithmetic operations. Now that we have discussed the ones complement and how signed integers are encoded or modeled into computer memory, let's shift our attention to try and answer the question of what would be the maximum or minimum such number using ones complement for signed integers. In other words, by considering the ones complement format for 2-bit, 3-bit, 4-bit, etc., can we again extrapolate the pattern to determine the minimum and maximum number for the general in-bit word? We start by enumerating all the 1s and 0 combinations of the 2-bit, 3-bit, and 4-bit ones complement format. We then write out their respective ranges as a sequence to observe a pattern amongst the maximum as well as the minimum. This is achieved as follows. Similar to before, we look for powers of 2 among the range maxima sequence to see if we can easily spot the generating function for this sequence. The term values for this sequence is generated by the formula t to the n minus 1 minus 1, where n is the number of bits. In other words, this formula gives us the most positive integer that can be represented using n bits. Similarly, the minimum is attained using the formula 2 to the n minus 1 minus 1 made negative. It is negative 2 to the n minus 1 minus 1. Notice that for the exponents to line up with the indices of the sequence, starting at index 2, we have to subtract 1 from the exponent n. This corresponds to the following fact about the contrast between unsigned integers encoding versus 1's complement format, where the range differs by 1 element. Thus, there is one fewer unique element in the range of signed integers than there are for unsigned integers, but this makes sense since we crossed out the all ones number to obtain the invertible relationship between the number sets when looking for an appropriate encoding of the additive identity element. This brings us to the conclusion of episode 3. In the next episode 4, we will talk more about 2's complement format, which is just another alternative way that modern chipsets encode negative integers that gives us an extra negative so that the 2's complement and unsigned integer format have equinumerous range.